we want to find the equations of all of the vertical tangent lines for this equation, 2x minus 3y equals x squared minus y cubed. So if we want to find vertical tangent lines, what does that tell you? It tells you that the derivative needs to be
undefined.
Okay. So in order to figure out when the derivative is undefined, we probably need to figure out what the derivative is. So we'll use implicit differentiation on this. So 2x should just give us 2, right? And then minus 3y ought to give us minus 3 dy dx. And then the x squared ought to give us 2x, and the minus y cubed ought to give us minus what? Ought to give us 3y squared
dy dx.
dy dx. Good or no?
Good.
Okay. So then we'll subtract, let's say we'll subtract this 2x to get 2 minus 2x equals 3 dy dx minus 3y squared dy dx. And if I were to factor out the dy dx on the right-hand side, what would be left over there? A 3 minus 3y squared times it. So I could just divide by that 3 minus 3y squared and get a derivative. Everybody feel okay about that derivative?
Yes.
Okay. So vertical tangent lines, derivative is undefined. Well, that will happen when the denominator is equal to 0, right? That'd be when y is
Positive or negative 1.
positive or negative 1. Good. Now, there is an important thing that we need to worry about here. And if we talk about vertical tangent lines, it means that the derivative is undefined, not indeterminate. Okay. It cannot be 0 over 0. It has to be a constant over 0. Now, when y is 1 or negative 1, we don't know what this numerator is, do we? Is it possible that that numerator is also 0 when y is 1 or negative 1?
Yes.
Possible, and it's not necessarily true, but it's possible. How are we going to figure out if that numerator is 0 when y is 1 or negative 1? We need to figure out what x is, right? When y is 1 or negative 1. And so in order to do that, we need to plug it back in to figure out the x values. We're going to need to do that anyway, because we want to know the equations of the vertical tangent lines, and vertical lines have an equation of x equals something, right? X equals some constant. So regardless of whether or not we needed to check this numerator, we also need to plug this in to find the x values to find what those vertical tangent lines actually are. Does that make sense?
Yes.
There are 2 reasons to plug this back in up here. So let's do that. Let's start with 1. If we do y equals 1, that's going to give us 2x minus 3 equals x squared minus 1. For x squared minus 2x plus 2 equals 0. Everybody agree with that?
Yes.
All right, and then we'll solve this quadratic. The easiest way to do this is to not do it at all, but we'll do it a little bit. This gives us a negative 2 if we bring that over, and then we can complete the square, right? How do you complete the square with something?
Divide b by 2 and square it.
Right, divide the b value, which is negative 2, by 2, so negative 1 and square it. gives you 1. So we're going to add 1 to each side, and then this will factor. But the problem here is when I try to square root, on the right-hand side, we get the square root of -1. So that gives us no real solutions. So we would find out that there aren't actually any places on this equation where y is equal to 1. So we can ignore y equals 1. Then let's go in and do y equals -1. That ought to give us 2x plus 3 equals x squared plus 1. Everybody agree with that? And that'll give us x squared minus 2x minus 2 equals 0. And we can complete the square by adding a 1 in here. And when we simplify this, we get x minus 1 squared equals 3. X minus 1 equals plus or minus root 3. And x equals 1 plus or minus root 3. So these should be the equations of our vertical tangent lines, as long as neither of those x values make the numerator equal to 0. So what x value is the only x value that would make this equal to 0?
1.
Only x equals 1 would, right? X equals 1 would make it indeterminate, and neither of those is x equals 1, is it? 1 plus root 3 and 1 minus root 3 are both not 1. So these should be the equations of our vertical lines right here. And we could go in and take a look at this in Desmos. What was no, I forgot. What was our original equation here we had? 2x minus 3y, I think.
Equals x squared minus y.
minus 1 cubed.
Great. All right. And so this is what that equation looks like. It's like this little egg-shaped thing, sort of, and this little v. And we'll note that when we plugged in y equals 1, right, we got that there were no real solutions, and that makes sense. At y equals 1, there are no points. And we ended up with x equals 1 plus square root 3, which is this vertical tangent line right here. And we got x equals 1 minus square root 3, which is the vertical tangent line over here. Tangent to the curve at this point and tangent to the curve at this point. Good or no? Any questions or issues with that?
No.
Let's do another one. This time we want both the horizontal and the vertical tangent lines. So first we'll find a derivative. What's our derivative going to be? That'd be 4x minus
4x minus 12y squared dy dx
equals what?
equals 3x squared minus 2y dy dx.
Everybody good with that?
Mhm.
Okay. And then let's see, well, let's just get all of the x's to one side and all of the y's to the other side. So that'll be 4x minus 3x squared. And then 12y squared minus 2y. And both of those are being multiplied by dy dx. So I could factor the dy dx out if I do that. Good with that or no? Yes, no, maybe. Everyone all right with that?
Yeah.
Yes.
So now we want horizontal and vertical tangent lines. So which one do you guys want to start with?
Horizontal.
All right, horizontal tangent lines. So if we're going to do horizontal tangent lines, that means we need to set either the numerator or the denominator equal to 0. Which one?
Numerator.
Numerator, right? So 4x minus 3x squared equals 0. Factor out the x, and we got 4 minus 3x. And so what two x values do we potentially have a horizontal tangent line at? 0 and what's the other one?
4/3.
Negative.
That's right. All right, so we're going to pause there for just a second. And let's do the vertical tangent lines. We'll do those ones over here. Vertical tangent lines. We need to set our denominator equal to 0. Factor out a 2y. And that gives us y equals 0 and y equals 1/6. Good or no?
Good.
Good.
Great. So now what we need to do is we need to figure out what y values do we get if we plug in 0 for x, and what y values do we get if we plug in 4/3. And then we need to figure out what x values we get if we plug in y equals 0, and figure out what x values we get if we plug in 1/6. So let's start with plugging in 0. Plugging 0 for x, what is that going to give me? Negative 4y cubed equals negative y squared. Or 4y cubed minus y squared equals 0. Or y squared times 4y minus 1 equals 0. Or y equals 0, y equals a 4. Everybody agree with those?
Yep.
All right. So let's do 4/3 real quick, and then we're going to talk about all of these. So at 4/3 for x, that's going to be a little bit more of a pain. 4/3 squared is what, 16 ninths, so 32 ninths there, minus 4y cubed, and then x cubed, that's going to be 64/27 minus y squared, which is going to give us 4y cubed minus y squared, and then 64/27 minus 32 ninths, I believe, is negative 32/27. And that's kind of a pain to try to solve, right? Would you agree that's a little bit of a pain of a cubic to try to solve?
Yes.
Yeah.
So we're going to, right now, we're just going to use Desmos to help us evaluate that. Okay. So we'll learn how to do it with our regular graphing calculator soon enough. So what's the equation? 4y cubed minus
Y squared.
y squared. Was it minus 32/27 or plus?
Minus.
Minus 32/27 equals 0. It's not going to tell us. Darn. All right, never mind. We're going to have to do it in terms of x. All right. So if we do it in terms of x, was it 4x cubed or 4y cubed?
Yeah, it was.
There we go. I don't know why I had it equals 0 there. We'll just graph the equation in terms of x. That ought to give us the x-intercept at 0.761. So we're going to learn how to do that on our graphing calculators later on, but to save time now, we're just going to do it with Desmos. 0.761 is where that crosses through. So this is y equals 0.761. So if we look at all of the different values that we've got here, if we plug in 0 for x, we get 0 for y. What does that do to my derivative?
Makes it indeterminate.
Makes it indeterminate. So this one we can ignore. And then what about if we plug in y equals a fourth? Does that make the denominator 0? Or 0.761? Neither of them should, because both of the values that make the denominator 0 are 0 and 1/6. So we should have 2 horizontal tangent lines. Good or no?
Good.
All right. Now let's do the vertical one. So if we plug in 0 for y, what do we get? 2x squared equals x cubed. Or x cubed minus 2x squared equals 0. Or x equals 0, x equals 2. Do you guys agree with that?
Yep.
Okay. What's going to happen if y is 0 and x is 0? This one's going to be indeterminate. So we can ignore that one. But x equals 2 and y equals 0 doesn't make it indeterminate, it just makes it undefined. So this will be one of our vertical tangent lines. And then we'll do the same thing for y equals 1/6 that we did. We'll plug in that and we'll get 2x squared minus, let's see, this is 1 over 216 is 1/6 cubed. So that's 4 over 216. What is that? That's 2 over 1 over 8 or 1 over 54, right? And then equals x cubed minus 1/36. So we're going to have x cubed minus 2x squared. And then we have minus a 36th plus a 54th. Let's see, that's 3 and 2. That should be minus 1 over 108. Hopefully you're all checking my arithmetic on that. Did I arithmetic correctly? Yes, I did. Okay, great. So now we will graph that to see when that is equal to 0. And maybe there's 2 places. Let's see. Oh, no, looks like that one is not. That one's just below. So we only have the one at 2.002. So this gives us x equals 2.002. And that will be our other vertical tangent line. We have 2 horizontal tangent lines and 2 vertical tangent lines. Everybody good with that whole process there?
Yeah.
Cool. Let's graph this and see what it looks like. So we got 2x squared minus 4y cubed. What was it? Equals x squared minus y cubed, I think.
Yeah, that's it.
2x squared minus 4y cubed equals x squared minus y cubed.
I thought it was x cubed minus y squared.
Oh, okay. I was gonna say this doesn't look like that looks much better now. All right. Sorry, when I pull up Desmos, I can't see the screen, the other screen at all, so makes it hard for me. I know you guys are probably, hopefully, writing down notes and stuff as we go. So, all right. So what were our horizontal tangent lines? We had y equals what?
1/4.
1/4 and
we zoom in there. Sorry, what? Yeah. What was the other one? 0.761.
Yeah.
Yeah, so there's the 1/4. That one looks like it certainly is, right? So that worked out nicely. And y equals 0.761. Yep, right up there, horizontal tangent line as this goes up to a max and starts curving back down. And then if we zoom in over here at 2, which is where our vertical tangent lines are, we said we had one at 2 and one at 2.02. And if you zoom in just enough, you can see that, yep, that is going just to the right here as it curves back, isn't it? Just to the right of 2. And so it would make sense that there would be one at 2, which, it's going to be really hard to see that just on our little interval here. It's going to be really hard to see that. But I think hopefully you could imagine that that is what's going on there. There's one at 2 as it goes, sorry, one at 2.02 right here. And then over here, it comes back, hits 2, and then comes back the other direction to show us that there's one at 2 as well. Good or no? Cool. Everybody feeling all right about this? A lot of work there maybe, but conceptually okay?
Like, will we be able to use like a calculator for like some of the ones that are literally like impossible to factor or something?
Yep. You'll be allowed to have a calculator to solve those equations. All right, let's do another one here. Let's see, this says find the locations of them, but let's just find the horizontal and vertical tangent lines. This one actually, I think the derivative is a little more complicated, but the work comes out a little bit easier and nicer for this one. So first thing we need is a
Derivative.
derivative. Derivative of 2x squared is 4x. And then minus 2xy we'll have to use the product rule for. So one function will be minus 2x and the other function will be y. So minus 2x times the derivative of y. And then plus y times the derivative of negative 2x, which is negative 2y. And then the derivative of y squared is 2y dy dx. The derivative of negative 4 is 0, and the derivative of 0 is 0. Right? The derivative of 0 is 0.
Mm-hmm.
Right?
Yeah.
Derivative of 0 is 0. Correct? Everyone agrees with that?
Yes.
That the derivative of 0 is 0.
The derivative of 0 is 0.
All right, cool. You might think I'm crazy, but I'm just going to say that a couple more times. And you're going to think that I'm crazy, but that's okay. The derivative of 0 is 0, right? I'm not crazy. I'm not losing my mind. The derivative of 0 is 0. True?
Yeah, I think so.
All right. Okay, good. All right, just make it sure. All right, perfect. Don't worry, I haven't lost my mind. I promise. There's a reason I've said that like 12 times. Derivative of 0 is 0, right? The derivative of 0 is 0. Yeah?
Yes.
Max, I'm asking my 7-year-old. Max,
Yes.
what's the derivative of 0?
0.
All right, good. Okay, he got it right. Good. Okay, he's requested that I not look at what color of colored pencil he's sharpening right now. Sorry for the sharpening sound in the background. So now that we've determined that the derivative of 0 is 0, let's solve for dy dx. So on the left side, we got 4x minus 2y. And on the right, we can move these other ones over. 2x minus 2y, and they both had a dy dx attached to them. Everybody agree with that?
Yeah.
Okay, so we end up with 4x minus 2y over 2x minus 2y is our derivative. Or if we simplified that a little bit, we could get 2x minus y over x minus y. Good or no?
Good.
Perfect. All right. So now comes the extremely important part of this. How do I deal with figuring out when The numerator is 0 and the denominator is 0, because this one's different than what we had before. When will I have horizontal tangent lines? When the numerator equals 0, right? Well, this one's different, isn't it? This is y equals 2x. This is giving me two different variables there, isn't it?
Yeah.
Yeah. That's a problem. How am I going to deal with that problem?
Do you substitute your original equation?
Yeah, we're going to take this y equals 2x and we're going to substitute it in up here to our original equation. Now that'll tell us at what values of x is this true. So if y is 2x, we'll have 2x squared minus 2x times y, which is 2x, plus 2x squared minus 4 equals 0. So what does that give us? That gives us 2x squared minus 4x squared plus 4x squared. Well, what's 2x squared minus 4x squared plus 4x squared? That's just 2x squared. Equals 4. Or x equals plus or minus root 2. Everybody agree with that?
Mm-hmm.
All right. What about for the vertical tangent lines? We'll come back to this in a second. For the vertical tangent lines, we got x minus y equals 0 or y equals x. So I could just replace all the y's with x's. 2x squared minus 2x times x plus x squared equals 4. So 2x squared minus 2x squared will cancel. I just have x squared equals 4 or x equals plus or minus 2. Well, these are good. Those are my vertical tangent lines, right? X equals 2 and x equals negative 2. But I still need to find my horizontal tangent lines. They can't be written as x equals, can they? They have to be written as y equals.
Yeah.
So how will I do that?
Substitute in the other equation,
So substitute where?
y equals 2x.
Yeah. So there's two places we could plug this in. We could plug this in up here, and it would give us the right answer. But we could also just plug it in to y equals 2x, because I know this also has to be true. So y is equal to 2, sorry, plus or minus 2 root 2. And those should be our horizontal tangent lines. Everybody good with that?
Mm-hmm.
Cool. Let's graph. Anybody know what this graph looks like?
No.
No, that's a shame. It is an ellipse. It's an ellipse. What was it? 2x squared minus 2xy, right? Plus y squared minus 4 equals 0.
Yeah.
Yeah, just an ellipse turned on its side there, rotated on its axis a little bit. And we had x equals 2, and we had x equals negative 2. There's our vertical tangent lines. And we had y equals 2 square root 2. There's a horizontal. And we have y equals negative 2 square root 2. And there's our vertical. We can see touching at all of those nice little points. Good or no?
Yep.
Awesome. Any questions on any of it? All right, we're going to move on to something a little different now. All right. Nobody's got any questions on the horizontal and vertical tangent lines? Okay, good news then. Let's move forward and find some second derivatives implicitly. So if we want to find a second derivative of an implicitly defined equation, what do you think we need to do first?
And the first derivative.
First derivative.
Find the first derivative. So to find the first derivative, we take the derivative of both sides with respect to x. This should be a pretty straightforward one since I didn't give you anything complicated in that. Everybody agree with that so far? Does that look good to everybody?
Yeah.
Nobody has issues with that? Okay, cool. All right. Now, what we want to do is find the second derivative with respect to x, which means we need to take the derivative with respect to x of both sides. So our second derivative ought to be the derivative of this. How do we take the derivative of 2x plus 1 over 1 minus 2y?
Quotient rule?
Quotient rule.
Quotient rule, exactly. So denominator times derivative of the numerator. What's the derivative of 2x plus 1?
2.
2 minus numerator times the derivative of the denominator. What's the derivative of 1 minus 2y with respect to x?
Negative 2 dy dx.
Exactly. Don't forget the dy dx. Right, we're still taking the derivative of a y term with respect to x, so you have to attach the dy dx. Good. And then all over 1 minus 2y squared. The denominator doesn't get a dy dx because we didn't take the derivative of it, right? It's just squared. And this answer would be wonderful if only I didn't have this dy dx term. Well, luckily, I know what dy dx is, don't I? I'll just plug it in there and replace it and get 1 minus 2y times 2 minus 2x plus 1 times negative 2 times 2x plus 1 over 1 minus 2y all over 1 minus 2y squared. And you don't need to simplify it any more than that. The only thing that you could do anyway would be to multiply by 1 minus 2y over 1 minus 2y over here so that you could get a common denominator and drop it to the bottom. But I don't need you to do that. Any questions on that one?
If you had more dy dx terms in the second derivative, then would you still just plug in dy dx into those, or would you factor it out in the second derivative?
Yep, you would just plug it back in the next time. So like if I had one over here, I'd just put it in for that one also.
Oh, okay, so you wouldn't need to factor anything.
Nope, nope,
Okay.
because these are not second derivatives. These are just dy dx's.
Oh, like the value itself.
Right. And
Oh,
so
okay.
you just plug it in with the dy dx's. Yep.
All
And if I asked you, suppose I asked you to find a third derivative, well, that'd be a horrible pain. But you'd take the derivative of this using the quotient rule with respect to x. And so any of the things with y's, when you took the derivatives, would get dy dx terms still. So you'd still just be replacing them with this.
Okay.
Does that make sense?
Yeah, thank you.
No problem. All right, let's do another one of these, and then that'll be good on these for today, and we'll move into something else. And this one will have multiple dy dx's within the second. So how do we take the derivative of xy with respect to x? What rule do we need to use?
Product rule.
Product rule, good. So that ought to become x times the derivative of y plus y times the derivative of x. And then minus 2y dy dx, and then minus 1. And the derivative of 0 is
0.
Wow, the 7-year-old standing in my kitchen dancing. Did that faster than you guys. We already went through that like 15 times earlier. Very disappointing. All right, what do we have for the rest of the way here? We need to solve for dy dx. So we'll have x minus 2y times the dy dx. And then on the other side, we'll bring over the 1 and the minus y. Everybody good with that or no?
Good.
All right. How do we find the second derivative then? We just take the derivative of our first derivative with respect to x. So the denominator times the derivative of the numerator, which is
Negative dy dx.
negative dy dx, and then minus the numerator times the derivative of our denominator, which is 1 minus 2 dy dx, all over that denominator squared. Good or no?
Good.
And all we have to do is replace the dy dx's with
0.
not 0 this time, with our value for dy dx, which was 1 minus y over x minus 2y. I got a little messy there because I ran out of room. Sorry about that. Any questions on that? You feel okay about that?
Nope, sounds all looks good.
Nobody's got any issues? Everyone's good. Cool. All right. That's implicit differentiation and second derivatives using implicit differentiation. We're going to move on to some other rules for derivatives now so that we can apply them into the chain rule and apply them into implicit differentiation. So some derivatives of some slightly more complicated functions. So we're going to start with exponential functions. In order to do that, we are going to start off by looking at this very simple function, e to the x minus 1 all over x. And I want to ask you, just at a cursory glance at this graph, what do you think that limit equals?
It looks like it equals 1.
Looks like it equals 1, doesn't it? You guys all agree with that? Sure looks like 1?
Yep.
It's 1.
Zero.
There's no good way for us to prove this limit yet, although there is a nice easy way to prove it soon, sometime after we come back from Thanksgiving, but we're going to need this limit today sometime. So the limit as x approaches 0 of e to the x minus 1 over x is 1. You don't need to memorize that, other than for the next 5 minutes. You need to just keep that in mind. After that, you can sort of forget about that. So now what we want to do is see if we can find the derivative of e to the x.
One.
How are we going to find this derivative? Any thoughts?
Yeah. But you can see that it looks like a Y.
Can we like manipulate the other thing so that it becomes the quotient rule for
You mean this
finding
thing
the-
over here?
Yeah.
No, we can't. That's a good idea. Unfortunately, we can't do that. You can't move stuff around within the limit to like the other side or something to try to simplify. Then no, we're not gonna manipulate it in that way. We just want to find a derivative. We have a rule to find a derivative of that.
We use the product rule. Wait, no, the power rule.
Okay, power rule. That is not the way we're going to do this, but that is the way that most people always say, power rule, because it looks like it, right? Right? X e to the x minus 1. Unfortunately, that does not work out. The power rule only works if we have x to a power. So if I had x to the e, sure, that'd be e to x to the e minus 1, right? Because that's a variable to a number. But anytime it's a number to a variable, we cannot use that rule. So we don't have a rule for it. Power rule is not going to work. There's no product. There's no quotient. It's not a function within another function. So if we don't have a rule for it, the only way we can really go about finding this is with a limit. And what limit will we do to find the derivative of something?
Limit of x approaches h of f of x plus h minus f of x all over h.
The limit is h approaches 0 of f of x plus h, so that'd be e to the x plus h, minus f of x, so that's e to the x all over h. Good or no?
Good.
Okay. Is there any way at all to simplify this? Because if I plug in 0, I get 0 over 0, I get indeterminate. So what? What can I do? How can I rewrite this in some way?
You can expand e to the x plus h by saying e to the x times e to the h.
That's a great idea. Let's do that. Based on exponent rules, right? If I have e to a plus b, that's the same as e to the a times e to the b, right? If you're multiplying with the same base, then you add the exponents. And so now what can I do with this? Now the numerator has something in common, right?
Can I get the answer? Can I get the limit?
What can I do with this numerator?
Factor out e to the x.
Take out the e to the x, leaving me with e to the h minus 1 over h. And now what do we notice?
Isn't it still indeterminate?
It's still indeterminate, yep. What do we notice though? How quickly you all forget.
That one thing where it equals 1. I mean, it doesn't have x, it has h instead, but isn't it still 1?
Right, as long as this is an h and this is an h and this is an h, which it is, that part of it should all be 1. So I could rewrite this as two separate limits. The limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the h minus 1 over h. And this first limit as h goes towards 0, what is e to the x? should just
to
be
x.
e to the x, right? And what's this limit in the brackets on the right?
1.
1. And so 1 times e to the x is just e to the x. And so we've gone through and we found the derivative of e to the x. And the derivative of e to the x is e to the x. That doesn't seem right, does it? Well, it is.
The limit is constant x with respect to x.
Okay, so the derivative of e to the x is e to the x. You need to know that. You need to memorize that. That is important to know. Good?
Good.
Weird? Slightly weird that the derivative is the same function? Right? I could throw like a 2 in front of there. Like the derivative of 2 e to the x would also be 2 e to the x. So the derivative of 7 e to the x would also be 7 e to the x. But other than all of those functions like that, where where e to the x's derivative is e to the x, there's only one other function that when you take its derivative, you get the same function. What is that thing, that other thing that when you take the derivative of it, you get the same thing you started with?
0.
0. There was a whole reason why I repeated that like 1,000 times, right? The only other one is the derivative of 0 is 0, right? So the derivative of e to the x is e to the x. The derivative of 0 is 0. Those are the only functions that you get the same function out when you take their derivative. Pretty cool, huh?
Yep.
All right. So we should be able to apply the chain rule to the derivative of e to the u, e to a function, right? We could rewrite e to any power as e to the u with u equal to that power. And then the derivative would just be this times the derivative of the exponent. Does that make sense? This is just the chain rule application of it. Good or no? Okay, so the derivative of e to the x cubed plus 5x can be broken down into y equals e to the u with u equal to x cubed plus 5x. And as we just talked about, the derivative of e to the u is e to the u, and the derivative of x cubed plus 5x is 3x squared plus 5. So our derivative should be that 3x squared plus 5 times e to the x cubed plus 5x. Good or no? Any issues with that? You feel okay about that or no?
Yeah, makes sense.
All right, why don't you guys try and do the second one on your own, and then we'll talk about it. I'll give you like a minute to work on that. Ready, go. All right, so this is e to the u with u equal to x squared plus sine x. So we just do the derivatives of each. The derivative of e to the u is e to the u, or e to the x squared plus sine x. And what's the derivative of x squared plus sine x? Ought to be 2x plus
Cosine
of x. Everybody good with that?
Yes.
All right, cool. So e to the x is a good function. It's a good one to know. We need to know that derivative. You need to memorize that derivative. But we also might not just have e to the x. What if we had a to the x, any constant? So any positive value of a other than 1. Any thoughts on how we'd go about that? Anybody?
Could we use the same method that we used for e to the x?
We could. The only problem with that is that A could be any number, not just E, right? A could be 2, or it could be 7, or it could be 3/5, or anything like that. And then that limit that we used as part of it, the limit is x approaches 0 v to the x minus 1 over x. That does not have a specific value that it equals for all of those functions. So unfortunately, that won't work out. Other ideas? All right, is there any way to rewrite a to the x? Sounds like you guys need some help here. How can we rewrite a to the x?
0.
All right, let's start with something easier. Is there any other way to rewrite this?
Is that just the number 7?
That's just the number 7.
Like 4 plus 3?
That's true. That'll work. Not the one I was looking for. All right, well, I'm going to keep the 7 there. If this looked like something like this, e to a power, couldn't we take the derivative of it?
Yeah.
All right. Could I write 7 so that it looks like e to a power?
Seven times e to the 0.
All right, we could, yeah, I mean, that's still the same thing, but that didn't rewrite the 7 per se. That's true, that's still equivalent, but. Isn't that the same as 7? E to the natural log of 7?
Yes.
Yeah, that's something you should have learned, right? E to the natural log of 7 is 7. What's e to the natural log of 3?
3.
3. What's e to the natural log of x?
X.
X. So how could I rewrite a to the x using this idea?
You get a to the x.
Y will equal what?
A to the x.
E to the natural log of a to the x.
E to the natural log of a to the x. Everybody agree with that?
Yeah.
And how could I rewrite that? What can I do with this x that's a power inside of a logarithm? You guys know your log rules, right? What can I do with this power that's inside of a logarithm?
Can you move it to the front?
I can. E to the x natural log of a. And now I have a fairly simple function here. Y equals e to the u, with u equal to x, ln a. And I should be able to take the derivative of that, right? By taking the derivative of this, which is e to the x natural log a, and multiplying it by the derivative of x natural log of a. Well, what's the derivative of x times the natural log of a?
It's
All right. What is natural log of a? What is A?
Would the derivative just be 1?
Nope, nope, nope.
Would it be a derivative of a constant?
X is not a constant, so. What is A? Just what is A? A is a number, isn't it?
Yeah.
True. What's the natural log of a number? It's another number, right? So what do I have? I have a number times X. Suppose that number was 2. What's the derivative?
2.
2x. What's the derivative of this?
7.
What's the derivative of this?
A.
Pretending that's a pi, right? That's pi, right? Well, if natural log of A is just a number, what's the derivative of just a number times x? It's just that number. Is that okay with you guys or no?
Yeah.
All right. So this is our derivative. It's e to the x natural log A times natural log A. But it'd be cool if we could rewrite e to the x natural log of A. Right? What is e to the x natural log of A? It's the same as e to the natural log of A to the x, which is the same as a to the x. So we can say this derivative is a to the x natural log of A. Which, if we think about the special case that we did earlier, right, with e to the x, isn't e just a number that's greater than 0 but not equal to 1? So the derivative of it should be e to the x times the natural log of e. Well, earlier we just got e to the x. That's okay because natural log of e is just
1.
1. And so this is just e to the x. So it works for e to the x as well. So as long as a is any number greater than 0 except for 1, the derivative of a to the x is a to the x times the natural log of a. Good or no?
Good.
All right. Could we apply the chain rule with that? The answer should be yes, right? If we want the derivative of a to a function, a to the u, then it should be a to the u times the natural log of a times the derivative of that function. So here, 3 to the sine x is y equals 3 to the u, with u equal to sine of
X.
Okay. And so the derivative ought to be the derivative of 3 to the u, which is 3 to the u times the natural log of 3 times the derivative of sine x, which is cosine x. And 3 to the u is 3 to the sine x. 3 to the sine x, natural log 3 cosine x. Good or no? All right, last problem of the day. This is 7 to the u with u equal to x squared cosine 5x. So the derivative ought to be 7 to the u times what? What does our rule say?
Natural log of 7.
Times the natural log of 7 times the derivative of u, which I'm going to have to use the product rule for. So that's going to be x squared. And then what's the derivative of cosine 5x? Well, that's cosine v with v equal to 5x. So the derivative of that ought to be negative sine 5x times the derivative of 5x. So negative 5x squared sine 5x plus 2x, the derivative of x squared, cosine 5x. Good or no?
Wait, just real quick, where did you get the 5 in front of the x squared again?
Chain rule on the derivative of cosine 5x. So cosine v with v equal to 5x. So negative sine of 5x for this cosine part, and then times 5 for the derivative of v.
Okay, thank you.
Yep. Any other questions on that?